Hi. In the last video, I prepared a block level design of how I was going to read the serial EEPROM and move that data into SRAM. There were some challenges making sure that I got all my thoughts straight and presented them effectively, and I don't know that I did a great job with that, so my apologies there. Today's video, I want to continue with that thought, and I want to find all of the pieces that I can consolidate into a single breadboard or single PCB and use that as the control circuitry for the control logic. There's at least one issue that I'm aware of in this block level design. I'll show you that, and I'll explain my comment about a guarantee to either be successful or guarantee not to be successful. Let's get into that. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. Okay, here's where we left off at the end of last video. And I'm not going to spend a lot of time staring at this particular block diagram, but I do want to identify the components that are really one-offs that can be moved to the control circuit, where I have left over just the bits that have to be replicated for each control ROM individually. So the D-type latch that indicates that I'm in reset, the copying set reset latch, the 74HC157 ICs, and all of the counter ICs very easily move to the control. Additionally, if you look at the 74HC165, that IC is responsible for sending the read command and the starting address to the serial EEPROM. And then it's no longer really required, it just needs to be passing in some value as it goes through the reads. So that one can also be centralized or moved to the control circuitry. And so that's what I'm going to pull into the emulator and start with. I'm going to start with the control ROM control circuitry and make sure that I get that working properly before I start working on any of the individual control ROMs themselves to make sure that they work properly. In order to do that, I need to develop out a 74HC157 IC for the emulator and a 74HC165 IC for the emulator. Let me get that done, and then I'll come back and we'll talk about exactly how this is coded and how to see what's going on. Let's start with a quick code review on what I had to build in order to get these operating. I did create a 74HC or XX03. Now this is a open collector, open drain, depending on which technology you're using, AND gate. It's very similar to a 74HC08 as an example, except instead of outputting high, it outputs high impedance. It is able to pull the line low. And so I literally did a direct copy of the 74XX08 ICs and then changed the states so that everything was outputting Z instead of high. Now, the 74XX157 is a quad 2-to-1 multiplexer. So depending on whether or not you're selecting input A or input B is what's going to be passed on to the output. Now, this is going to sit between my counters or my instruction. One's going to be A, one's going to be B, and then the output of that is going to go to the parallel SRAM. I also created a 74HC or LS, depending on which technology you like, 165. Now this is a parallel load shift out register. And important note here, we are shifting out the QH side of things, which is the most significant bit, depending on how you wire up the parallel load. But it does shift from A to H, and H gets shifted off the IC. Now I've got regular C implementations of each of these, and again, there's nothing that's earth-shattering here or significantly different. But I did also create a module for my control ROM control. Now this is intended to be a single PCB eventually when we get there. And so I have all the different ICs that are going to go onto this. And again, as I indicated in the last segment, all of these are going to be duplicated exactly once and shared across all the control ROMs. So my address, my shift in register, which is shifting to the serial EEPROM. I did put a clock on here because I want the clock to operate far faster here than it does in the actual build. I got some LEDs on here for debugging and troubleshooting. If I come down here to the actual C++ source, my constructor is built off of a group box, and I allocate all my components. So these are all the news. Then I build the GUI, I wire it up, and then I trigger first updates to make sure that everything's in sync. And then I set my clock interval to be 0. Now, I want that clock to run as fast as possible. And the emulator, that clock will be basically as soon as it completes, it's going to trigger again. And the wire up was fussy, but I did use the block level diagram that I have to perform this and check each one of these signals to make sure that they are wired up properly. Nothing majorly different than what I've done in the past. The register module uses exactly the same situation here. In order to support this, I did change the computer hardware a little bit. I added the module in here. So I did create 2 additional buses. One is an instruction bus. Now this is a bus that comes off the instruction register into the address that is going to be looked up into the control ROM. There's really one input and one output from this, but I'm going to call it a bus at this point, just for the ease of coding. The second is the control logic lookup bus. Now this one comes off the outputs of the 74HC157 ICs and goes off to each of the individual SRAM. Now this will be a single input out onto the bus, or a single assert out onto the bus, and several reads from the bus, and it will never really change other than when we're in reset and we're copying data versus not. Ultimately, what's going to happen is the 157 is always going to be asserting something out onto the bus, and everything else that has interest is going to be reading. Again, this just makes coding a little bit easier for this. It's going to look very close to a bus when we get it into the build, meaning that it's got to go through the backplane to get from one module to another. So with that, let's run it. Now, in the interest of full disclosure, I have run this, and there were a couple of GUI elements that were missing, so I did go ahead and correct those, but I know that there are issues here. So I will shrink this down, and you can see my clock, and I hope the frame rate's picking this up properly. My clock is running like crazy. I am in copy mode, but my reset is cleared, and I do not have the correct address down here. It's certainly not incrementing like I thought it would. If I click the reset button, circuit does not go into reset at all. That light does not turn on. So most of what we're going to do is going to be focused down here in the bottom left-hand corner, other than pressing this reset button. But I'll focus in on this corner to make it a little bit easier to keep track of what's going on. And we'll start ticking off these issues one at a time. And that's going to require some debugging code. Now, just so you understand, I don't typically use an interactive debugger. I am a logger type debugger, which means that I like writing code to output text that I can then read and compare back into the sequence that I expect things to happen in and check values as I go along the way. I could use an interactive debugger here, but I don't do things linearly like that. I need to be able to jump around a little bit and see what's going on. So I will bounce around in the logs quite a bit to check things and go back and revisit things that have passed. If you're an interactive debugger type, I applaud you. You do far better at that than I do. My sense is always to go for the logs first. I do it in my professional life, and I do it here when the things that I work on here as well. All right, time to write some debug code. Okay, let's start with the reset sig. Now the reset is handled by a 74HC74 dual D-type latch. Those have been used in the flags as well, so it's not likely that the problem is going to be in the IC, but rather in my implementation here in my control ROM control module. Now, if you look at that, pin 1 and 2 of this IC are handled in this signal called private signal internal reset. At the bottom down here, when I process the reset, I am actually emitting this private signal internal reset, but I don't believe I have anything that subscribes to that. I define it in the header as a signal. I've got a couple of things that are referenced by that, and then just the emit of the signal. So that should be a relatively simple thing. I just need to create some connections to this internal reset event. Okay, so if I reset, that still is not showing reset here. So now I got to write some debug code. So let's go down to the bottom here, and let's just make sure that I'm actually getting that signal. So I am getting resetting. It's not setting the reset, but if I press and hold resetting, that's accurate. It's not setting the reset latch. Ah, I see it. Okay, and pretty much what I did is from the beginning, I set this up so that it would clear the latch in the 74HC74 IC, but then expect the output of that to be high. So what I really need to do is I need to preset that value, which happens asynchronously. Okay, let's fix this in code. So my clear, which is on pin 1, needs to really be preset, and then this needs to be clear. Now I'm just backwards on my LED. What that tells me is I don't need the inverted or the preset. Let's check my signaling here because I might have that backwards. It's an active low signal. Ah, I wanted to change this to be an active high. I'm going to hold off on that change for the moment until I get this debugging done. So the change that I made here is a good change for now, but knowing I'm going to have to come back around to that in a few minutes and change that once I get the rest of this debugged. Well, that didn't work. There it is. And the key to that is if I have to invert my reset signal going into the preset, I also had to invert my data coming back out. Both of those will have to be changed when I reshape that reset signal. The next order of business here is going to be to debug the load of the address counters down here. The address that should be loaded is 7FFD, and obviously I've got 7FF0. So I'm not exactly sure what's going on with that. We need to get to the bottom of that and find out what's going on there. To do that, I'm going to start by looking at the value that's being loaded. The low order nibble from most significant bit down is high, high, low, high, which is in fact D. So that should not be an issue. The question is am I getting a good load signal? That goes straight to the 74HC193 IC, and I need to set up some specific debugging for that. The thing to pay attention to here is that the 74HC193 IC is actually used in several different places, so I've got to make sure that I don't get anything that I don't want included in the debug. So in order to do that, I want to check the load, and so I'm going to make sure that the name of the object is specific for debugging. So now if my object name is specifically debug, then it will output the fact that it's trying to load. Now I have to set up the object that I want to debug, and I want to watch the lowest address 0. And so this line then turns on debug for that particular object. Let's run it. Okay, so I'm seeing a lot of loads here, and it's happening very regularly. So I've actually got my load tied to something it's not supposed to be tied to. Let me go check that out. So here's the line in question for the least significant nibble. And coming straight off the 74HC74, the inverted output is tied to the load. Now, what I'm not certain of is how this is being handled and if I'm actually trapping things that might be duplicates. So I may be getting extra signals coming off the 74HC74. And so let's take a look at that. So there is a rising edge detector built into that, so that should not be what's causing the problem. So let's add some more context here. And we're going to output the state that we are changing to as well. Let's give that a shot. Now, once again, I don't expect it to be any different in behavior. I should only see values here. And I'm getting highs only, so that is good, but I'm still getting a pass on to, so there's still some signal here that's coming through. I'm still only triggering on the rising edge, so that's not going to tell me anything. I still have something that's causing a rising edge to take place. So I've got to go back to my 74HC74. Aha. Okay. So there's the problem. My oscillator is actually producing a clock signal. I'm not checking the prior state of the output and only signaling when the output changes. That's actually a good optimization for the 74HC74 IC. So by only changing or only signaling when this state changes, I will reduce a lot of noise, and that will address the problem I have with extraneous signals here. Okay. Now I could put this as an additional AND condition in this if statement, but I believe it's a little bit more clear what I'm trying to do by separating that out. Let's give that a test. Okay, I'm not getting repeated loads. I still don't have the correct value, but I've at least gotten to the bottom of that issue, the repeated loads, something I didn't realize I had. Let's go back to the load. We do need to try to get to the bottom of that. And what I'm going to do is I'm going to actually create myself a little bit of room here, because ultimately I want to also include the value that's being loaded into this. So I'm going to expand out this inline function a little bit, make it a little bit longer than I would normally, but it's in the interest of getting to the actual value that's being loaded. Let's build that and see what we end up with. Okay, let's give this a shot. So I'm loading a value of 1. Let's break this down into individual bits, and let's include the state. So I only output this when state is high. Okay, so yes, I am loading the correct value. Okay, so now I've got to figure out why the LEDs are not displaying the correct value. I'm getting the correct value loaded into the counter IC, but the outputs are not correct. Let's go find a reason for that. Okay, the address LEDs are likely to be down here where I am wiring up the LEDs, and I probably made a mistake somewhere along the lines. Okay, these are coming from the 74XX157 IC. That one could have a problem. It could be an issue with the AB select, or it could be that things just aren't asserting properly from through the bus. I doubt it's the bus. Ah, I see it. It's a copy and paste issue. That might work. Let's give that a shot. Okay, I'm now getting a value here, which is good, and that's now the correct value when I actually manually reset it. So the question is did I get some kind of a clock tick in there that changed it before it should have? That's entirely possible. But what I don't see yet is the bit counter, which is supposed to count the bits of the byte, and I'm not sure that that's working correctly yet. So I'm going to add some LEDs into this so that we can see the bit counter and assess where we're at with that. Okay, let's give this a shot. Now the bit counter should be decrementing, which means that I am expecting the 1 bit to flash. but I'm expecting the 2 and the 4 bits to flash a little bit less frequently. So something is not right. This could be with the counter because it's the only counter I am using to count down. So the counter I see itself could be flawed. Let's slow the clock down. Where is that? Set clock interval. Let's change it to, let's make it a second. I'll end up changing that back relatively quickly, but let's see what that gives us here. And yeah, just as I thought, my 1 bit is flashing, toggling, but my 2 and 4 are not. So let's go find the reason for that. So by now you should probably be asking, Adam, how is it that you know that the problem is not with your design? How do you know the problem is with your emulator? And it would be a fair question to ask. And the response I would give to that is, it's probably the emulator, because not everything has been exercised properly yet. That doesn't mean that my design is not flawed, but I'm going to go with looking at the emulator first, because that's where I can discern the most. And then if I eliminate all the possibilities in software, then I have to start really looking at the design. So if I am down counting, I do decrement. And then I do signal that it's been updated. And then I set all the bits appropriately, and I emit my signals as needed. All right. Let's add a debugging line in here. And this is going to tell me what the count is so I can see if it's cycling or what's happening there. Now this is only going to happen on a down count, which I am not using anywhere else in the build, so I should not need to bracket that for debugging. Let's cross our fingers and see that hope that I'm right here. So it's not actually down, well, that's interesting. It's stuck on 6. I'm not sure why it's going back to 7, other than maybe it's getting a load when it shouldn't. So let's take a look at that load pin. So it is down counting properly, but I'm probably loading it too frequently. Let's double check that. Okay, and load is ended with borrow out should be high unless the clock is low on the IC and the contents are 0, which means that it's getting ready to borrow. All right, let's do this. I'm going to change the debug associated with that load line from address 0 to bits. And let's see what we get. Wait a minute, what just happened here? -1, -1, 0, 0, and then 6. But I'm not getting the loads happening. Yeah, that's 193, so I'm never actually loading the 193. Okay, that's interesting. All right, let's go look at the inputs into AND1, gate 2. Those are correct. So the other thing to think about here as I go through this is the first time I have wired a 74 HC193 back on itself in the emulator. And the question then becomes, is it actually working properly? So in other words, I am now, do I have a timing problem? And this goes back to my comment in the last video. Am I guaranteed to have success or am I guaranteed to have failure? And I believe it's one of the two, and it's all related to timing because this is all very linear in nature. If I was to build a stack of the function calls and the pins that got updated in the emulator, you would notice that it would flow down an entire call stack to its ultimate conclusion and then return back up that call stack and then turn around and do the next leg of that call stack, trying to get to the point where it was updating everything. And it's entirely possible that I've got things arranged in such a way that something turns on and something turns off before the condition is totally met, such as this AND gate. And then it doesn't actually end up working the way that I intended to. And I'm not saying that that's exactly what's going on here, but it's entirely possible that I have something like that that I need to take a look at, and maybe a fundamental flaw in this entire emulator at this point. I'm not certain. So I'm going to pause recording here. I've got to do some thinking on this, on how I'm going to get to the bottom of this particular concern. And maybe it is handled differently than what I've got set up here. Let me think. While I was editing the last segment, I did notice the problem that I identified at the end. And so while I stepped away for about 30 minutes and did something else and came back and edited that segment, it dawned on me exactly what the problem is. Now, this is going to be systemic. It's going to be more than just this one place. I'm going to have to pay a little bit more attention to what's changing and how it's changing and how I perform the updates. But under every circumstance that I enter this block of code, I am updating the borrow out inverted, meaning it's an active low signal, and emitting the fact that it has changed. When in fact, probably the majority of the times that you are in here, it will not actually have changed. So I'm getting a signal that there's a change and that there is a new value associated with it, and I'm not actually having to change something. So the solution here is to check before I actually do anything. Okay, so now that signal is being emitted only when there is an update. Now, I have the same problem up here with the carry out, so I will make that change here as well, so that that is cleaned up. I'm going to have to go through every IC that I've built so far and check that I am only emitting change notifications when changes actually happen. There's going to be a lot of those. All right, that said, well, I tell you what, I see another one, two more right up here. Let's get those cleaned up. Okay, now that said, let's run that and see how that works. No change in behavior, so that's not the root of the problem. That's not to say that it isn't part of it, but there's more going on here than just that. Okay, let's take a look and see what's going on with this load signal. Now, load is handled here, that it actually loads the state and then processes this updates complete function. That's this function here. If clear is high, it sets everything to low. If load is low, then it sets it appropriately. And this is an issue here because what it really is supposed to do is it's supposed to ignore everything else that's going on because the load is asynchronous and it overrides everything. So with that, I need to put all of those other conditions in an else clause, and maybe that will at least correct the behavior. Okay, this loads 7, which is correct. It does not decrement, which is not correct, but it is now at least consistent behavior. All right, let me try one more thing here. And I'm going to stick one up here for load. And I am expecting that to show up with every clock cycle. And that's exactly what it's doing. What does that mean? That means my load signal for the bits counter is always low. Let me get a truth table out. Here is the truth table for the load signal I worked out in the last video. This is not correct. So let's take a moment and revisit this and redo it. Whenever I am actively in reset, or when QR is high, I need that load signal to be low. Doesn't matter what anything else is doing on the system. When borrow goes low and we are not resetting, then I need that signal to be low. Otherwise, I need that signal to be high. Well, the good truth table and the bad truth table look very similar. I just have that resetting signal wrong. I should be taking the inverted Q output off that D-type latch. Let me make that change. Okay, so here we are back in code, and really the 74HC74, I should be taking the Q1 inverted output here in order to perform that reset. Let's test it. Let's fail. That is still not correct. I am still getting a load with every cycle. Well, using the debugging techniques that I have demonstrated so far, I wrote in quite a bit more into this counter IC, the updates complete, and there's certainly a problem here. And let me see if I can walk you through it. This may take a minute. So on each entry, and I'm specifically trying to track the borrow flag, I'm writing out that I am entering into the counter and I output the state of the borrow flag. So during the initialization down here, I'm seeing that things are changing. Borrow is set to 1 along the way as we go. Now for each condition other than clear, which clear wasn't relevant for this, but for load it is relevant, I'm outputting that I'm loading a new value and what the state of the borrow flag is when I do that. If I update carry, I indicate that I'm updating carry and what the state of the borrow flag is. If I have a borrow situation, I'm indicating that I'm in a borrow situation and I output the state of the borrow flag. Same thing with the up counter, same thing with the down counter. And so what that gives me is a way to trace this through. I've still got other things in here such as the AND gate, which indicates the state of the the delatch, and indicates the state of the borrow flag coming off the counter, which is what B2 is here. All right, so I'm still initializing borrow as 1. Then I end up in a borrow situation and borrow gets set to 1 or is still set to 1. Then I end up loading and I go into this routine and I'm loading a new value, but borrow has now been set to 0. And so one of the things I notice is that on load, I am not resetting the borrow flag. If any change has taken place, I need to reevaluate the borrow and the carry flags. Now, what I believe has happened is that I end up with a clock tick here. The value of the counter is still at its initialization state, which is 0, and the clock goes low, so that qualifies as a borrow. So it is resetting that borrow flag. And indeed, this 0 here is the value of count. So it is properly setting that flag, but it's not resetting it after the load. And so I believe that's ultimately what the root of my trouble is. And so I now need to look at rewriting or updating or changing this function so that it operates under all conditions and reevaluates the flags properly every time. This is going to be more than just a couple seconds of code, so let me get that done. I'll come back, I'll show you what the resulting code is. We'll test it for the first time together. Pretty much a major rewrite on this function. So now I am going to make use of the fact that I only supply the emits when things have actually changed. On a clear, I no longer touch the input pins. I only update the output pins, leaving the inputs asserted the way that they are. And then only when things change do I emit signals. And I put the IC into a known good state. Notice I'm paying close attention to the borrow out pin because if I clear it, it's set to 0. On a load, I'm doing pretty much the same thing I did before, but now as part of the exit of the function, there's a lot going on now in which I'm calculating the new carry out, the new borrow out, the new QA, QB, QC, etc., and then checking for changes and updating them accordingly. Finally, I record the last up and down state. All right, let's build this and test it. And isn't that embarrassing? Because it's still the same problem, except I'm not copying anymore. So whatever I've done is taken me out of the address reset. So that's not a good thing. If I messed up my program count, my carry is not happening, which means my borrow is probably not happening either. All right, let me put the debugging code back in. Okay, one more quick test because I realized I was not updating the borrow and carry in every case. So let me just remake that and retest that. Okay, well, my counter is now working properly. I am loading the right value in the address. I'm just simply not counting, or I'm still stuck in reset. Okay, after a little head scratching, I came back here and apparently I did not ever properly update or save maybe my change to switch to QR inverted instead of the QR for the AND gate. Now when I run it, I am now decrementing. That looks like it's resetting properly, the bit counter anyway. And my address counter is counting down. So let me improve the speed of that. And that does look successful. Now, it is taking what I would call forever in order to actually get through all 32K of memory. And I'm obviously going to have to pay attention to that. But I've got the basis for copying the memory from EEPROM into SRAM. Okay, well, I didn't get quite as much done in this video as I had hoped. There is still a little bit more testing to do, and I want to compare the behavior of the emulator to the breadboard. So I am going to put a bunch of this circuit on breadboard, or at least bits of it, for testing, just to make sure that I get the results that I am looking for. Now, while the address is up here, wrap up here in the corner, next video I do want to focus on getting this converted into a schematic and completing that testing. And then, time permitting, I am going to try to extend that out into a complete breadboard build. Well, it sounds ambitious at this point, given what we've been through so far in this video. Let's see how far we get. See you soon.